In Chapter 5, we're going to take a pause on statistics portion of the course, and we're going to build up the probability portion of the course. So to do that, we need to think a little bit about what probability is. So let's explore what measurement is. It seems like a simple idea, but measurements were invented out of necessity so that we can compare things. So considering the following measurement situations. Is a classroom that you're sitting in, is that wider or longer? And what tool could you use to find out? Well, you'd be measuring length then, and you'd use a ruler or a tape measure, string that you would, count the inches, count the feet, count the yards, etc. Does it take you longer to run a mile or eat a pizza? Well, if that's the case, you're measuring time, and you'd use a clock or a stopwatch, and you'd measure yourself. Right? Hopefully not eating too many pizzas in order to measure that, but you'd be measuring it nevertheless. But it's a time thing you're measuring. But then what about the chances of rolling boxcars in a game of craps, or randomly drawing an ace out of a deck of cards? Well, that's talking about the future, right? And you're trying to measure that future risk, that future unknown. And when we do that, we use probability. Probability is our tool of measuring. It's a numerical measurement, but about the future. And that makes it quite tricky to think about. It makes it difficult for us to process. And this is what we're going to learn about in Chapter 5. And the answer is that sometimes we use, well, how the die is built or how the deck of cards is built to be able to figure things out. And sometimes we use past data to make inferences about what that future is going to look like. So those two types of probabilities are kind of be going hand in hand with us through Chapter 5. And then through Chapter 6 and 7, because we work with probability for a few chapters here. All right, so let's move to applying the rules of probability. So we need to learn some basic definitions. A probability experiment is any process with uncertain results that can be repeated, anything you can do more than once. And the probability is the proportion of times the event occurs in the long run, as a probability experiment is repeated over and over and over and over again. And a measure, its probability is a lot of things that are wrapped up in that definition. So it's a measure of the likelihood of events that have yet to occur, right? Measurement of future. The symbol for it is a capital P. So the probability of an outcome O is abbreviated capital P for probability of O, event O, or outcome O. We write probabilities in a few different ways. We write them as decimals, we write them as percents, and we write them as fractions. And the vast majority of the time, we're actually going to write them as decimals because decimals are the easiest of those three number types to work with. All right, and then the sample space is the collection of all possible outcomes. So let's see an example here. We have a fair six-sided die. I have this rather large die in my house. And we are going to record the side that faces up, which is a pretty typical thing. You roll the die, whatever side is facing up, like in this case it was a 1, that's what you're recording. So to say that it's a fair die, what does that mean? Well, in probability, that means that every side was just as likely as every other side. In other words, each side is equally likely. The die is not loaded, it's not weighted to roll on one side versus another. It's fair. Every side is just as likely to happen as every other side. All right, then we want to determine the sample space. Well, the sample space is the list of all possible outcomes. If you're going to toss the die one time and record the side facing up, it could be a 1, 2, 3, 4, 5, or 6, and that's your sample space. Now, an event is any collection of outcomes from a probability experiment. An event may consist of one outcome or many outcomes. In general, events are denoted with capital letters, such as capital E, E for event. So if E is an event, then we write P parentheses E as the probability of event E, or of the event E. A simple event, by the way, is an event that only has one outcome. So for example, rolling a 1 is a simple event because there's only one way to do it, rolling a 1. All right, so let's define the event E is the side facing up is divisible by 2. Divisible by 2 means that it's even. So there are 3 sides that do that, 2, 4, and 6. So event E is 2, 4, 6. So then the probability of E would be 3 out of 6. There's 3 sides that are even out of 6 sides total. We could reduce that to a half. That'd be the fraction. Or we could write it as a decimal, 0.5, or as a percent, 50%. All right, now let's look at the first of the two methods we're going to use to come up with probabilities. So there's the empirical method. Now, empirical method means we're going to take empirical evidence. We're going to take data and from the past and make inferences about the future. So obviously this is a very important and potent thing for us to work with in statistics. So we take the number of times we have observed event E and divide it by the number of trials, and we say, ta-da, that will be our probability, more or less, right? It's the relative frequency, that's a typo in there, frequency of E. So we learned in chapter 2 what relative frequency is. That's when you take the total, right, and that'll be your denominator, and then you take the number that are in your group and divide it by that total. So obviously this is often used in statistics because we often have a data set in statistics to make inferences from for the future probability. So for example, we have the following table shows the number of graduates from Jackson College from spring 2010 to winter 2011 by degree. So what we would want to know here is we want to know the total. So let me add that in down here at the bottom real quick. So the sum is equal to 1067 if I'm not mistaken. I'll double check that. So I can check this by adding them up with my calculator here real quick. 511 plus 97 plus 24 plus 228. Oops, it's 1077. I was wrong. Sorry about that. Okay, so that sum is 1077. So now I'm going to use that to find my answer. So I'll take 66 and divide it by 1077. And that'll get me about 0.061. Let's do 3 decimal places here. And then I'll do it again and again and again. So let me fill out the rest of these. There we go, we have it. So I rounded to 3 decimal places here. So 0.061, 474, 090, and so on. So each time I'm taking this numerator and dividing it by the grand total. And normally you don't actually have to show all the division. I'm just showing it to you in the notes here so you know where it comes from. Let's see what that right-hand column adds up to. So if I add up those numbers, I get 0.999. Now don't be worrying about that too much. Notice it's very close to 1. Oops, sorry about that. So, and that makes sense because we would expect it to be about 100% when we're all done with this. Right? So it's okay that it makes 0.999. That's because we've rounded. All right, so we have all the rounded probabilities. Everything's good. Explain why these are empirical probabilities. Well, they're empirical because the numbers come from actual data from the college, right? None of it was hypothetical or, let me put it this way. Hypothetical is the later probability we're about to learn. So when we don't have data, it's all kind of set up as a hypothetical. We don't have that. We have real data, and that means that it's empirical. All right, now, are any of the degree types unusual for JC graduates? Well, remember back from chapter 3, unusual means, recall, oops, I don't know why I'm green there, hold on. Recall from chapter 3, unusual means less than 5%, okay? So do we have anybody that is less than 5%? Sure we do. We have the associate in science right there. That's less than 5%. And concentration, that one's less than 5%. And those two are the only ones. So both of those would be considered unusual because they have a less than 0.05 probability. All right, so we're all done with that first empirical probability section. Now let's look about the classical probability section, which is that hypothetical probability I was talking about earlier. This is where you assume that all the elements of the sample space are equally likely, and then you figure out the probability from the number of outcomes you have in event E divided by the total number of outcomes in the sample space. This is a much more difficult probability to find because everything is hypothetical. You don't have any data to rely on. So this is very much important for gambling because gambling, cards, dice, things like that, it's all based on a hypothetical. I assume each card is equally likely. I assume the dice are fair, etc. So the fundamental assumption for classical probability is that everything is just as likely to occur as everything else. Everything's fair and balanced. So suppose you're going to draw a card from the standard 52 card poker deck. So here's a standard 52 card poker deck. You are expected to know the suits, which is spades, hearts, clubs, and diamonds. You're expected to know the face cards, which are the jacks, queens, and kings. You're expected to know, 10, 9, 8, all the denominations. You're expected to know the colors. Spades and clubs are black, and hearts and diamonds are red. You're expected to know how many total there are. So if you feel the need to play solitaire a little bit on your computer, so be it. In order to be able to understand the card deck, it is important to us. All right, so let's look at what's the probability of a 9 of diamonds. So 9 of diamonds is right here. It's that card right there, 9 of diamonds. So there's one card out of the 52 total. So that would be a grand total of 1 out of 52. All right, what about the probability of a black card? Well, there's 26 of them, right? 13 spades, 13 clubs. So that would give us 26 out of 52, which would reduce to a half if you were going to do as a reduced fraction, or 0.5 if you so desired. I know it said to leave it as an unreduced fraction, but I just want you to see how you can break these down. So that'd be 0.5 or 50% even. All right, now what about the probability of an ace? Well, there's 4 aces, ace of spades, ace of diamonds, ace of clubs, and ace of hearts. So that would make 4 out of 52, which would reduce to 1 over 13 if you wanted it to. Now, a face card is any card that has a face, literally like an eyes, a nose, and a mouth. So that would be the jacks, the queens, and the kings. They're faces. The ace is not a face card. It's often a high card in different games, but it is not a face card. So there are 12 face cards total in this deck out of 52. Right? So that would make 12 out of 52, which is 3 out of 13. All right, now what about the probability of a red spade? Well, the red spade is impossible. So the probability equals 0. Let me put it this way. If you have something that's impossible, it has a probability of 0. There we go. All right, now if aces are low and kings are high, which is actually the way I have this drawn right here, what's the probability of an ace or higher? Okay, ace or higher, so that'd be from here on up. So that's all of them. They're all there. So that would be all the cards. So the probability is equal to 1. All right. Now explain why this is classical. All these probabilities that we found, these are all classical. That's because we didn't do an experiment. We don't have any data to draw from. We're just assuming that every card is equally likely, right? Based on the makeup of the deck, based on what the cards look like. We just assume they're all just as likely as any other, and therefore that's classical probability. It's not based on a data set. Should be what I'd say here. In other words, we had to draw, we do not have a data set to draw the probabilities from. We only have our minds and the setup of the example. There we go, and the problem setup. Oh, oops, that didn't fit in there. There we go. Now this leads us to another conclusion, which is that there's a couple things going on here that we should probably pay attention to. Namely that there are some rules for probability. The lowest a probability could ever be is 0, the highest it could ever be is 1, and all the probabilities in the whole sample space have to add up to 1. And that's where we'll pick up next time. I'll see you then.